Quite often in many applications you have lots of data, you have images, you have voices and so on. And if you try to directly work with these data coming from hospital, coming from patients, coming from different applications, if you try to directly work on them, you will have lots of trouble. So you need to transform your data to some simplified form of data, some canonical form in order to. So you need some pre-processing in general. So one of them is linear transformation, which could create some interesting properties on that. So linear data transformation is that one of the objectives could be that the data are not usually orthogonal, or they are heavily correlated, they are heavily redundant. So each sample is repeating information from the previous sample and so on. So we may want to make them orthogonal. We may want to reduce their interdependency, and also we want to preserve all the necessary and sufficient information without loss of anything. So the orthogonality of input data simplifies many algorithms, such as determination of the projection of a hat. So if your input data, they are orthogonal, that means that its autocorrelation matrix is diagonal. So you don't need to inverse the matrices. So you don't need to perform complex processing. So one of the things that in many applications they do, they linearly transform their data in order to decompose the input components to make them orthogonal. So linear data transformation is that you have an input vector data, you multiply it by a matrix, your output is just a matrix, this t is constant, and it is supposedly that t is inversible. So from y you can also get x, so it is sufficient and necessary to process y. So if we could design these system such that the components of y are uncorrelated, if the component of y are orthogonal, then it is easier to process them in parallel. If they are less redundant, if there is less dependency on them. So this is the objective of linear data transformation, some of the objectives and so on. So you could try to say, oh, I have a vector x and I want to find t such that the transformed data vector has some property. So y is a linearly transformed version of x, and instead of processing x, we want to process y, and we want to find t such that entries of y are orthogonal. Or we could even put another constraint to say, oh, want entries of y to have unit length. So they are like a set of vectors which form input data. So, and then process the orthogonal data. So this could be an objective that we'll give one example. And there are various algorithms that they do that. One example of this algorithm is Gram-Schmidt orthogonalization that we will give a little bit more details. The Gram-Schmidt orthogonalization is not the best one in most applications, but this is easier to understand, but you can use the other ones which are more useful. You don't need to do these things.